Hello, so today we are going to take a look at this problem called advantage shuffle. So what the problem says is we get two arrays as input. They have the same size, A and B, and we want to return a permutation that maximizes the advantage of A over B. And advantage here, what we call advantage, is if at a position I, the value A sub I is bigger than B sub I, right? So at a position, if the value in the array A is bigger than the value in array B, then that means A has an advantage, and what we want to return is a permutation of A such that it has the maximum possible advantage over B. So if we take an example here, we have two arrays A and B. The way to maximize the advantage of A is to permute A here to this version. If you take a look, we would have 3 bigger than 2, we'd have 12 bigger than 11, we'd have 8 bigger than 5, and we will have 16 bigger than 12, right? So by just putting A, changing the position of A and 12, we have the maximum advantage because now A at every position is bigger than B, right? The second example here is we have this array A and then the array B. If we permute A to this, we get the max advantage. You can see here 7 is bigger than 3, 11 bigger than 5, 23 bigger than 12, 22 bigger than 11, right? So one thing you may note here is that the result for us always made A be bigger than every value. Sometimes it's not possible. Sometimes maybe we had here, let's say 1, then maybe it's not possible to find, like we can maximize, for example, by having the advantage be 3 times, be 3 here, but not this one. That's fine, but as long as we get the maximum possible advantage. Yeah, so this is the problem. Now let's see how we can solve it. Okay, so let's see how we can solve this problem here. So the main thing to think about here, okay, seems like what we want is to get A to be, every element in A to be bigger than B, or at least as much of that as possible, right? So let's take the first example here. So the example 1 we have was that A was equal to 3, 8, 12, 16, and then B was equal to 2, 11, 5, 12. So one thing we can think about here is, okay, what if we sort A and B, and then we can, if a value in A can't beat the smallest value of B, then that element is useless, like basically not useless, but that element can't win for us, right? So maybe we can, a good way to think about this is like, if AI is bigger than BI, this is what we win, right? This is where we can score, right? And so if we sort them, sort A and B, what do we get? So if we do that, we get A is going to be equal to 3, it's already sorted in this case, and then B is going to be 2, 5, 11, 12, right? So if we take a look here, if we had, instead of 3, if we had 1, let's say here we had 1, then we know one can't beat 2. So since this is sorted, 1 will never beat anything else in B, right? So that means the first element will always give us a loose position, right? So if we had something like this, 12, 16, 2, 5, 11, 2, 12, and we process here and we find, well, 1 is, so this would be A and this would be B. 1 is smaller than 2, right? So this won't ever win for us, right? Because as we go right, we'll only find bigger values, right? So what should we do with that value then, right? So one way to say is, okay, let's just let's just put it on in a list. Let's call the remaining elements that we haven't used yet, right? And then go forward, and then go forward here, and we will find that well, 8 is bigger than 5, right? So this element wins for us. And since it's the smallest, that means we better use it right away, because if we go right, we will only find bigger values, and bigger values have more potential to beat the other values of b, so we better keep the biggest values, right? And use the smallest one. So we use it, which means using it means that how can we keep track of those that 1 over b? Well, we could just have a map, right? So we could just have a map here, maybe call it assigned, right? Because let's say we assign the element at this position to this position here to beat to this element so that it can beat it, right? So if we call it assigned, then the element 5 here would have 8 assigned to it, right? Because that's what beats it. And then we go as well, we keep going. And now we are here, right? 11, now 11, 12 is bigger than 11, so it beats it as well. So we put 12 here, and then we go, we keep going. And now we are at 12 and 16, and 16 is bigger than 12, so it beats it as well. So we have 16 here. And now, so this was just our first pass. So with our first pass, we have the remaining elements, and then we have the assigned one. So this is with the first pass. And then we can do a second pass, right? And our second pass would be, well, just look at the array, right? We want to construct a new A, a permutation of A that beats as much as possible B. And so the permutation is going to be, well, for each B, check if it has a value in the map that we have. If it doesn't, just pick any value from the remaining, right? Because we are losing anyway. And so just pick any value to lose with, right? And so here, what this would mean is that, well, for the first position, for 2, well, 2 is not in the map, right? So we could just pick any value for it. And let's pick any value from the remaining, so we pick 1. And then we go. For 5, we look at the map. It's there. We take the value for it. For 11, we have 12, so we just put 12. For 12, what do we have? So for 12 in the map, we have 16, so we use 16, and this is the permutation that we need, right? So to recap here, remaining will just we'll just put there all the values that make us lose, right? The ones, because when this is the smallest and this is the smallest, if this can be this one, it won't be any value else. So we have to lose with that value. So we just put it there so that we can use it for any values that we didn't assign. And then we go and we check the next one, right? Is it bigger? That means it can beat it, so we use it. If it can beat it, we use it. If it doesn't, then we put it in the remaining so that we can use it later. And this works only because we sorted, right? Because if we didn't sort, then maybe we'll get 12 here. We would have 5, 11, 12 for B here. And we'll find, okay, 1 doesn't beat 12, right? So we just go, right? But that's not right, because, okay, let's say if we didn't sort, and let me pick a better example. So let's say if we didn't sort and we had 16, we had maybe, I don't know, 8 here, right? And then we had 12, 1, 16. And then here, let's say we had 11, 2, 5, and what should be this one? 12, right? So if we didn't sort, this would be A, maybe this would be B, and we will find that 8 is smaller than 11, so we'll get rid of 8. But 8 could have beaten 5 for us, right? So now we have 2 losing positions, 2 and 5, but if we had sorted, we would have only 1, right? So that's kind of the idea of how sorting helps us. And the approach we are using here is kind of a greedy approach, because we take the smallest possible for both and compare. If it doesn't work, we know it won't work we know that value of A won't win for us, and so we just put it in the remaining so that we can use it for the remaining values of B. Okay, so this is the greedy approach we are using here, and often greedy works with sorting, and so that's a hint for us to use sorting here, right? Okay, so now let's just go into this, write this in more detail here. Actually, let's run it on this example again, on this A here, just to get a better idea of what we are doing. So 3, 8, 12, 16, and B is 2, 11, 15, 12. So step 1 is going to be sorting. And B in increasing order, right? And so with that, we will get A is going to be 3, 8, it's already sorted, good. B is 2, 5 actually here, 5, 11, 12, right? So that's the first step, and then we would need a couple of other things here. We need the remaining. We'll put all the values that lose for us, and then we will need the assigned map, right? To keep track of which values we assigned to of A, we assign to values of B, so that they can be, so that we can beat them. So this is a map from B values to A values that can beat them, or that can win for us, right? And so here we just go through. So step 2 would be go through A, right? And then we need to keep track of the position we are at for G. For B, keep track of position at B with, just you could use G or whatever. So what this would mean here is that, well, I'm going through A here, and then I'm at this position for B, right? And so 2 is, I check, and 2 is, 3 is the value at A is smaller than 2. Is, sorry, bigger than 2, right? So that means it wins for us. So that means in the map here, we would have the value at 2 has 3 assigned, right? And then we go to, so that means we already assigned a value to this one at G. Just to make this more interesting, let me change this 5 here to 9. Right, so now we are here, our G is here, and A also we advance with the for loop. And so we are here, and we check, well, 8 is actually smaller than 9, right? So which means 8 doesn't win for us, so we add 8 here, right? And so now we don't advance J because we haven't beaten 9 yet, right? And so we go, and we have 12. Well, 12 now is bigger than 9, so that's good. That means we assign to 9 the value 12. And now we advance J. So you can see here we don't advance J until we find something that wins for us, because it's easier to find something that wins from A for a smaller value than from a bigger value, right? And so here with 11, well, we advance 12 as well because we use 12. 16 and 12, well, and 11, so 16 is bigger than 11. That means we assign to 11 the value 16. And then we assign the value, so we need to advance J. And we are done because A is over. We are going through A. We are going through A in this step, and so we are done here. We know that the remaining now is yeah, pretty much. So now we do the second pass. Here, put the ones we can't win with. In remaining list, and then the ones we can, assign them to B values in assigned map like we did there. Now the second step is to reconstruct the permutation that we are looking for. So step 3, using remaining and assigned map. Reconstruct the permutation using remaining and assigned map, right? So to do that, well, it's going to be just, well, let's take every position, right? Let's take, for each value of B, let's go through B basically. Let me write that down. So it's here, so go through B. That's the first thing. So we check 2 and check if it's in assigned. So if it is, that means we know what value is assigned to it. So 2 is an assigned. We know that the value is 3, then just add it, right? And then we keep going. But actually, there is just one caveat here is we want the permutation of the original B. So let's go through the original B, not the sorted one, just to get a nice order. So we go through the original one, 2, we find 3. And then we advance here to 11. Well, 11 also we have value 16 for it. So we add 16. We advance to 9. And 9, we have a value 12. So we add that. We advance to 12. And this is the interesting part. We don't have 12 in the map. So we just grab from the remaining any value because we are losing with that value anyway. So we grab 8. And with that, we are done. So this is the permutation. So here, one thing to clarify here is go through initial B before sorting. If there is no value in assigned, no. In assigned, use any value from the remaining. Okay, so yeah, this is pretty much the gist of the solution here, but the main idea is we sort both, and since we know if we have the smallest values first, compare the smallest value of A with the smallest value of B. If the smallest value of A can be the smallest value of B, that means that A value won't win for us at all because we tried it with the smallest value. And so we just put it in a remaining list, and then if we find, then as we go, if we find a value of A that is bigger than B, it can be it, we assign it to it, we save that in the map that we have here, and then at the end we have 2 data structures. We have the remaining list and we have the map of the assigned values. We go through the original B again, and for each value of B, we check if it's an assigned, we put that as the value at that position for A. If it's not in the assigned, we take any value from the remaining and put it there. And so that will maximize for us the advantage because there is no other way to find a better, like for the values that we skipped, the smallest one, there is no way to, because we stay at the value of B until we find one that beats it. That means the other ones, the bigger ones, if we can't beat them, that means we don't have a value to beat them with. And yeah, that's pretty much it, the solution here. Let's quickly write it down and make sure it works. So what we have here is advantage shuffle. We have A and B. And what we said is we need to sort both first, right? So we have sort for A. For B, since I'm going to use the original B for a sorted B instead. So this would be sorted B. And then we need to define the map here, the initial map for assigning A values to B values. And so here, this is just going to be a map. And just I'm going to give the default here to be a list. It doesn't, like, basically it can be just a value, but just for easy processing, I'm going to make the values here a list. And each value will contain only one, so that's fine. And then This is mostly for checking at the end if there is something to assign. And then I need the remaining, right? The remaining list. And now I do the step, so I did the first step. I need the second step, which is go through A. And so to do that one, we can just do for loop here. And what do we need to do in the first step? Keep track of position at B with G. So we need J to keep track of position for B. So let's just have a G here equal to 0. And now put the ones we can't win with in remaining, and the ones we can win with is in assigned. So let's do the check here. So if A is bigger than the current value we are looking at for B, right? This is what we did. We went through the sorted B one by one, right? And so if it is bigger, that means we can win with it. So that means assign it. So that means we assign to B the value of B, which is sorted B at position J. We assign the value A. And we increment, because we already assigned something for that value, we only need one, so we increment J, right? Else, what we need to do is, so in the else case, we can't, this is the smallest value, we can't win with it. That means we can't win with it at all after that, because the values of B will only get bigger, and so we just put it in the remaining. Okay, now after this, we do the third step. So let me just annotate these with what step they are. So this here was step 1. This here was step 2 to go through A. And now we do our step 3, which is constructing the result. And so to do that, well, we could just return. And let's construct the array here. So we want to get the value of assigned B. Since it's a list of one element, right? If there is a value, we can just pop that element, right? And this is, of course, only if there is a value, so assigned B. We could also do something here. Let's say, for example, we could check instead that the length is 1, right? Because if there is a value, then the length would be 1. If there isn't, the length would be 0, because the default is list. So we could say if, so we could say here, if length of assigned B at position at B, this is a map, right, is bigger than 0, we could, and this in Python is just similar to doing assigned B, pretty much. If it's empty, this would be false. So if assigned B, otherwise, what should we do? As we said, we should pick from the remaining. So we can just pick from the remaining and do that pop, which will give us the last element of remaining, right, in constant time. And then this we will do for each B. And so to do that, we will do for B in the original B. As I said, in this third step, we need to reconstruct the permutation, and we go through the initial B before sorting, right? And so that's what I'm doing here, and that's pretty much it. So if there is an assigned value, we just take that. Otherwise, we just take from the remaining, and that's pretty much it. Now let's check here for time and space complexity. So in terms of time here, we are doing sorting. So these two here, we are doing of like n time, of n like n. And such that A and B, since they have the same size, we can just consider n to be the size of A and size of B, right? So this would be 2n log n, which is just O of n log n. And here we are going through A, so this is O of n. And here, this is also going through B, so this is O of n. So of 2n plus O of n log n time. So overall time complexity here. So time complexity is going to be O of n log n, right? Now, in terms of space, we are using this map here. So let me just remove this. So in terms of space, we are using here O of n, right? This is at most the number of elements in A and B, so it's O of n, and we are using the remaining, which is also at most O of n, right? So space complexity here is just O of n. And also this one here, the result is going to be at most O of n, so we have overall O of n, right? Yeah, so that's pretty much it for this solution. Let's try it and make sure it passes some test cases. Okay, so let's see the solution here that we saw in the overview. So we sort A first, we get the sorted B array. We have our assigned map and the remaining list. We go through A, this is step 2. We check if A is smaller than the smallest value at B that we haven't processed yet. If it is, we check if A is bigger than the smallest value of B we haven't processed yet. If it is, we assign it to it. And we go to the next value in the sorted B. Otherwise, it's smaller, so that means it can't win for any other value in B, which means we add it to the remaining array here. And then once we are done, we went through the entire array A. Then we reconstruct the solution here by taking, if there is a value assigned for a value at B, we pop it and we use that. If there isn't, we just take any value from the remaining. Here we take always the last element, and we do this by going through the original array B, not the sorted B, right? This is just to have a nice order. And I have here some examples, and they should all pass. So let's see. Let's make sure they all pass. And we have all the tests is passed here. Yeah, so that's pretty much it for this solution. We'll take a look next at a more improved, or at least a different approach to solve this, slightly different approach. So with the second solution here, what we can do is change this solution slightly and use a little bit different data structure that make us use like a slightly better approach here. So what we can do is, instead of having an assigned map and remaining, we can just populate the new permutation of A as we go. So basically we would have an initial, have basically a res array here. So let's go, we would have a res array, right? This would be the final permutation of A that of course maximizes advantage. Advantage over B, right? Over B, right? So, and then instead of putting in remaining and assigned, we will directly put in res, right? The other thing is that instead of using a sorted B, we could use a DQ, because that will allow us to just pop the smallest in an easy way and pop the largest. And because if we have a double-ended queue like this, and it's sorted, right? So sorted DQ here, then we will have the smallest values first. So 2, 4, 5, 12, maybe 15 here. And so using, like, so if this is, let's call it, I don't know what, maybe call it BDQ or something like that, DQB, right? So if we do DQB, that pop left, this will give us smallest value of B. And then if we do DQB, that pop, we will get largest value. This is what we want, right? So how do we reconstruct a DQ so that it gives us this? Well, that's pretty simple. We could just, in Python, construct a DQ, create a DQ like this, right? And then put in it B sorted in ascending order, because we want the smallest value first. And so we'll put B for B in B, right? But there is a slight thing here, because I have a new result array, so when I'm putting a value, I want to know the index, right? So to do that, I'm just going to have my DQ here have two things. So for an array, let's say B, that is, if I take maybe 1, 7, 11, 15, we'd have 0, 1, 2, 3. In my DQ, I want to have something like this, the value and the index. And so I could have 7, 1, 2, 11, 2, and then 15, 3. Why do I want that? Because when I pop an element from B, I want to know what's the index in A. I should put the value that wins over this B value here, right? So to do that, what we can do here is say bi for I B in enumerate B, right? So we will get the pair bi, B is the value, I is the index, and then sort this, right? And put that in a DQ. Now we can do pop left to get the smallest value, right? Because we sorted, and we can do pop to get the largest value of B. Okay. Okay, so now we know we need two data structures, a result array and a DQ. Now how are we going to do the solution here? So the main idea is that we sort A and we sort B. So the algorithm here in this use case is sort A, right? And then create DQB, which is sorted B with sorted B with B and index, right? With index, with pair of value and index, and as a DQ, of course, right? So that we can easily pop the smallest and largest. And as we go through A, so go through A, so this is 1, 2, go through A, and do the following. If the value at A is bigger than the smallest value of B, right, which is, because of the DQ, the smallest value is just the first element. This is this array because we sorted it initially. So what is the value? The value is in the first position, so we get it with this. If that value is smaller, so that means the smallest value of A is bigger than the smallest value of B, which is the same as what we did in the initial solution. In that case, well, we can just populate res right away with the value because we assigned it, instead of waiting to reconstruct it in a second loop, right? So that's the main idea here. We are not going to do a second reconstructing loop. So we res, we get the index, since we have the index, right? We know the index, so we say, because we know the index of this value, of the value that beats B, so we can just say B 0 and 1, right? It's at position 1. And this will assign A, because we know it beats it. And then we will say else. That means it doesn't beat it, so this is, in the first algorithm we put it in remaining, but here we are going to do another greedy task, which is we can't beat anything with A, so we will know with this value A, so we know we have to lose it, so let's lose it on the largest value possible. This would mean that it will increase our chances of winning with the other values, right? And so to do that, we'll say, so basically use A for the largest value of B, not process it yet, right? So this would increase our chances, because if we take B and use it on the largest value, the other values are smaller, so that only increases our chance of winning over them, right? And so to do that here, how would we get the largest value? The index of the largest value, well, the largest value with the DQ is just this one. It's just the one we get with pop. Pop gives us the largest value. And so we can just use our DQ here and say, so sorry about this. This is DQB. I named it DQB. So let's call it DQB. And here DQB, right? And so That means we take dqb and we take the largest value, which here would mean, let's just pop it and get the index, which is at position 1. Right, maybe let me just write this in a better way. So here, current largest in B is going to be dq dot pop, right? So this will give the index is going to be at position 1, and so we could just say res current largest B1, and then that is going to be assigned A, right? So let me just do the similar thing here. So current smallest of B, since we want to remove it, right? We want to remove it, so we do pop left, because once we process it, we don't want to process it again. So we say dqb dot pop left, and then here we assign that value. So current smallest B at position, to get the index, we go to position 1, right? So position 1 is going to be equal to A, right? And that's pretty much it. At the end, we could just return res. Okay, so the main difference between this and the first solution is the part here where if we can't win with A, we use it on the largest value, because that will increase the our chances of winning with the other values of B, and winning over the other values of B, right? And so to do that, we use here data structure dqb, because that allows us to easily get at the same time the smallest value and the largest value once we put in the queue B sorted, right? And instead of using also a second path, we reconstruct as we go, and we create this res array to put values in. So this is the array, the permutation. Res will contain the permutation of A, and since we need to know the position, we just insert it initially here, and we go through sorted A. So here, let me just make this is clear. Go through sorted A. Okay, so let's write this down and make sure it passes test cases here. So this is advantage shuffle. We get A and B, and as we said, the first step is we need the result array, so we need to create a res, just our data structures here. So res, it just needs to have the same size as A. It can be initially just having none values, right? Range of length of A, and then we need our dq, right? So let's call this dqb. Is going to be, so it's going to be a dq here, and we want to put the sorted values, right? So we want to have sorted B, right? I, so this is the pair of the value and the key and the index for I, B in enumerate B. Okay, and now we can go through A sorted. So we can either sort it first or just say for A in sorted A. And now we can check if this first value of the sorted A is bigger than the first value of the sorted B, which is in dqb at position 0, right? The smallest value is first. If it is, that means we can immediately get it with dq pop left, right? So current smallest is going to be just dqb dot pop left, and then we could start assigning it, which means just say res at that position, which is current smallest at position 1 is going to be equal to A, and in the else case we can do we are going to use A on the largest value, right? So we'll also get the largest value by just doing current largest is going to be equal to dqb dot pop, right? This gives us the largest value. Let's use a on it because we can't win with this value a. So current largest index, this gets us the index, and we assign a to it. And once we are done, we could just return that value as we constructed. We don't need another pass. And that's pretty much it for this solution. If we take a look here at time and space complexity, you can see here in terms of time, we are using O of n here. We are sorting here as well. And yeah, that's pretty much it. So, sorting here, that's log of n. And here also we are sorting a, so O of n log n. So overall, it's going to be time complexity is going to be O of n log n. Now, what about the space complexity here? So for our space complexity, we have this dq here, which is going to be O of n at most. We have res array, same thing, O of n as well. So overall, our space complexity is going to be O of n as well. So space is going to be O of n. Okay. Yeah. So that's pretty much for this. So let's run it on the same test cases and make sure it passes. Okay, so here is a solution with the same solution as we saw in the overview. And so we just initialize the result array. We have, let's rename this to the same thing we saw in the overview, a dqb that contains b sorted. And then we go through a in sorted order. If the smallest element of a so far is bigger than the smallest of b, we use it. And so here we pop the left, which is the first element that we haven't removed yet, so the smallest one. We take the index and we make that the same index as for the permuted a, right? So maybe it's better, this res here, permuted a, right? We could call it res as well. And then we assign that value a. Otherwise, we pop the largest one. And since we can't win with a, we use that on the largest value of b, which would maximize our chances of winning with the other elements. And we return that at the end. Yeah, and as we said, this in terms of time is O of n log n. In terms of space, it's O of n as well. Yeah, so that's it for this problem. Thanks for watching.